McMaster University. We're very pleased to have him here. He is a well-known main contributor to network science, and in particular, theory of random graphs. And a lot of people are so happy to see your book. I think second volume already out there. A lot of new generation and old generation are using this book. So we're very pleased to have Remco with us. And
thank you very much.
Talk about fake news.
Yes, I will indeed talk about fake news. But before I get started with that, it's lovely being back here in Fields. I have not been back in 25 years, so it's wonderful to see old friends that I haven't seen equally long. It's also wonderful to see many other friends that I haven't seen in quite a while, and be back here in Canada, where indeed I have very long connections. Canada is a wonderful place. So I'll talk about fake news here. And you should bear in mind that what we're doing here is math. But it's inspired by applications. And I'll try to convince you that this actually is a good way of modeling fake news, at least when you're trying to be optimistic. It's hard to understand how you can be optimistic in terms of fake news, but we'll get to that. I like lively discussions, so I got a question whether it's okay for you to ask questions. Yes, please do. I'm giving this lecture for you, not for me. I'm supposed to know what I'm talking about, and I'm hoping that by the end of the lecture you also know what I've been talking about, rather than you being unclear as to what I've been saying. So if there's anything unclear, please stop me and ask your questions. All right, so first of all, this is joint work with Seva Schneer, Harriet Watt. We started with this in Russia, maybe very appropriately when talking about fake news these days. It builds on a lot of joint work with Shankar Bhamidi and Gerard Hooghiemstra. Gerard was my dear colleague in Delft. He's now retired, and Shankar, of course, is in North Carolina. All right, complex networks and news spreading on it. So, as I was saying, I'm trying to investigate fake news. And of course, we know that fake news is a huge societal problem and it causes major societal disruption. And the observation is that fake news spreads relatively quickly through networks. And we basically want to understand why that is the case. And therefore, we're going to be investigating this phenomenon. And what I'm particularly interested in is to filter out the network component of the fake news spread. So what part of it is due to the network, and what parts of it may be due to the fact that fake news may actually be more juicy than regular news, right? That is a part that I will not actually be looking at. I will really be looking at the network component of it. And that actually means that we're going to be looking at a model for the social network, which is a random graph. That will not surprise you, given the fact that I've been interested in random graphs for a long time. And we'll be modeling the fake news dynamics as something like a competing rumor spread through the network. And the vertices, after hearing fake or correct news, convince their neighbors at random and IID time. So this is sort of without the fake news component to it. This would be called first passage percolation, or SI, if you wish. And as I was trying to indicate, I'm advocating an optimistic perspective here, in the sense that once vertices hear the correct news, they'll actually immediately be convinced by it and will start spreading the correct news. Stop spreading the fake news. This is clearly not true in reality. Okay, that's why it's an optimistic perspective. Yet this allows us to look at sort of the whole spreading and fake news. Yes?
So the vertex can be in 3 states?
Yes, indeed.
Okay.
Yeah, so it can not have heard the news. It can have heard the fake news and then it will start spreading the fake news. Or it can have heard the fake news and the correct news, then it will be in the correct news states, and then it will be transmitting the correct news. It could also be, by the way, be in the correct news state without having been in the fake news state. That's actually what
yeah, but that's
a large
3 states, not 4.
Yes. Yeah, at any moment in time you have 3 states. Correct news is spreading, fake news is spreading, and we're assuming that the vertices do that all the time. But I will get to the precise model a bit later on. All right. So then networks. In this crowd, I maybe not have to say very much about networks. So I have two pictures here. I really like these pictures of the OptiPro project. Very artistic pictures of what the internet looks like. Now, what a large part of network science is doing is focusing on the unexpected commonality between the various different networks that can come from all sorts of different origins. Now, one of the commonalities is that many of these networks turn out to be sparse. So what I've done here is I've looked at Connect, and I had a very bright student who was actually mining this data. And what he did was he plotted versus sort of a log of the size. You see an exponential scale here. He was plotting the average degree in the network. And what you see is, well, of course, it's a cloud because these averages are not always the same, but there is no tilt to this. So it's not going up like this, okay? So that actually means that on average, irrespective of the network size, there is variability in the average degrees, but there is no reason to assume that the average degree will go up with the network size. I see a question there. Connect is a database of networks. So there is about, I don't know, well, certainly more than 1,200, but there's many more of them. And they're basically getting all of these networks from different publications on network science, and they list all the properties of these networks. So average degree, average distance, diameter, clustering coefficient, the sortativity coefficient, basically all the things that complex network theory investigates, they will be listed there. Yes, another question.
Size, is that vertex size?
Yeah, size, vertex size. No. So I'm really looking at what the average over the vertices is of their degrees. And this is the number of vertices that we have. Yeah. So, but basically what this says is that the number of edges grows linearly with the number of vertices. So they're of the same order of magnitude. Another question.
So does it have some real world?
Yes, real world networks. Road networks, I mean, all sorts of different things, but all from the literature. There's a vast amount of examples of networks that have been investigated in the literature, and they try to sort of put these in a database. Okay, now another thing that we see is that there is a huge amount of variability in the degrees in these networks. And that's sometimes dubbed as the scale-free paradigm. Whoa, what am I doing now? Okay, probably did something wrong. Okay, very good. So again, we plot here the log of the degree, here as well. And what we plot here is the log of the proportion of vertices that have that degree. And what you see is something that looks like a straight line. And when you start with something like this, pk is a constant times k to the power minus tau, you would get an exact straight line. Because then the log of pk would be a linear function of the log of k, and we're plotting the log of pk and the log of k here, okay? And even when such a relationship would hold, the slope of this negative straight line would be exactly minus tau. So the fact that these point clouds look somewhat straight line-ish has gotten people to say that you have power laws in these networks, because these are called power laws, okay? Now this is a controversial topic, because there has also been papers written that say scale-free networks are rare. But what we do see, and that's generally accepted, is that in many networks you see vertices with very high degree. So here it's sort of 10 to the power 3, here it's 10 to the power 5. That's actually rather substantial. And we've just seen that the average degree is actually bounded. Okay? So if you accommodate that, having at the same time vertices with very high degree, on the other hand, having a bounded average degree, it must mean that there's a huge amount of variability in the data. And when you have a huge amount of variability, it's very natural from a mathematical perspective to take these as a starting point. All right. So this is called scale-free behavior. It's not entirely clear where the name scale-free comes from, but one way of interpreting it is that if you were to look at your network and basically group together different groups of vertices of fixed size, collapse these vertices, and then look at the degree distributions of this collapsed graph, you will still see things that look very alike. You will still see the same power law exponent. So that's what is scale-free about it. Independent of the scale, you have the same power law exponent. Now this is another way of plotting this. Remember, we had this nice picture about the average degree here. Okay, the average degree doesn't really change very much. But here we see the maximum degree. And the maximum degree does change. It increases significantly with the size of the network. Of course, there is also a huge amount of variability. It's a huge cloud. It's not a straight line. You can't expect that. But at least it goes up. And my student did linear regression, and he found that the best possible explanation is that the log of the maximal degree, that's what Dmax is a constant plus something times log n. Okay? Now, let me write something on the board about this. So, suppose you are indeed in a power law setting. And now let's suppose that we're looking at power law random variables. And maybe the degrees in network should be thought of as being random variables. Okay? So what does this mean? It means that we're looking at random variables of the type that their tail distribution, so the probability of being larger than some value x, when x is very large, is roughly some constant divided by x to the power tau minus 1. You lose one exponent compared to my previous, because here you're looking at tails, larger rather than equal. Okay? Now suppose I were to have n IID of such random variables, and I would be looking at the maximum. This is a computation that is not very difficult to do, and what you'll see is that this grows like n to the power 1 over tau minus 1 times some limiting random variable which I'll dub y. This means that if I multiply mn by n to the power minus 1 over tau minus 1, then this will converge in distribution to a strictly positive random variable y. Okay, so this Dmax is the maximum of the degrees. Of course, they're not IID, but sort of pushing this a little bit forward, it seems to be suggesting that Dmax should grow like a positive power of n, where the exponent is actually related to the power law exponent that we've seen before. Okay? And that, of course, would mean that if I look at the log of Dmax, then this would be roughly, if I have a constant here, some other constant, plus 1 over tau minus 1 log n. Okay, that's exactly the type of linear relation that we seem to be having here. And also, it seems to be suggesting that 1 over tau minus 1 is roughly 0.519, and that certainly implies that tau on average is indeed in between 2 and 3. So you could say that this is a qualitative or semi-quantitative way of arguing that at least sort of on a large scale, these networks do have sort of growth of their maximum degrees as being a power of n, and that corresponds to a power law with an exponent in between 2 and 3. Now, why is this relevant? Well, if the exponent would be smaller than 2, then the mean wouldn't exist, so you would not be sparse. If the exponent is in between 2 and 3, these random variables are very special because they have finite mean but infinite variance. And that's sort of the hallmark of enormous variability. Central limit theorems, for example, do no longer apply. Okay? And if tau becomes larger than 3, then all of a sudden you have finite variance and central limit theorems will apply. Okay? So tau being in between 2 and 3 really is special. And also in network theory, it turns out to be a very special realm of, let's say, all the different random graph models. And we'll see that today as well. Very good. So I've explained you some background on networks. I've explained you in one very simple slide that was not mathy at all what I consider to be fake news. Let's now go in a little bit more detail. So first of all, I will say something about a network model. This network model is called the configuration model. This is one of the standard models in complex network theory. Raise hands if you've never heard of the configuration model. All right, then I don't have to explain very much. Okay, what I will be looking at, inspired by the first part of the talk, is that my degrees have an asymptotic power law. Okay? So in my configuration model, I have n vertices, n is my network size, n will tend to infinity in whatever I do. I will always be looking at large graph limits, and I'm assuming that my degrees are given. The degree of vertex I is going to be di. And then what the configuration model does is it basically pairs half edges. So you think of vertex j as having dj half edges incident to it, and you start pairing all of these half edges one by one. And it actually doesn't matter in which order you do it, because it will always give you the same answer, because this process is exchangeable. So that's basically what this says. Now, of course, what can happen is that in this configuration model, you're going to have self-loops or multiple edges. That's possible, and we'll just live with it. So we're going to be producing a multigraph with the prescribed degrees. If you don't like multigraphs, then you can sort of erase them, and you still get a random graph with basically the same degree distribution. Yes?
So for fake news, don't you want the underlying model to have a little bit of assertivity?
That's possible.
Like,
yeah.
Because we are more likely to believe fake news from people in our side than
Absolutely.
people in the
I'm
other
thinking
side.
about miscommunication or misinformation. Yeah. No, this is a very good point. In a certain sense, when you start sort of spreading your rumor from a source, the cycles don't really matter that much, because once you've heard it, if it comes to you again through another cycle, well, you've already heard it. But of course, in the real world, this is going to matter. Yeah.
What graph properties would matter? If it's a good expander.
A good expander is probably very useful. Yes, absolutely. Small world is probably also very useful, but these may be seen as coming hand in hand. Power law degree sequences, to some extent, because many of the results are actually also applying when you don't have them. Assortativity or clustering, I'm not entirely sure whether that would make such a big difference.
But you have confirmation bias, right? So confirmation bias.
Yeah, but bear in mind, I'm not modeling that. Yeah. If you would, then of course. But I mean, if you're really thinking about properly modeling fake news or polarization or something like that, I strongly believe that you should think of this as being a dynamic network effect, where you're also going to be rewiring your edges based on your belief, because you're going to like people with the same opinion, and you're going to dislike people with a different opinion, and they're no longer going to be your friends. In fact, this is what we've seen happening in the COVID period. So this model really is way too simplistic, but still it has an interesting story to tell. All right, very good. I will be making some assumptions about my degrees. I'm taking a large graph limit, so if my degrees don't behave nicely, then I have no way of taking any limits. And behaving, oh, okay, I'm doing something wrong. Behaving nicely means that somehow the degree distribution as a function converges in distribution. Now, if you don't like this, you can always extract the subsequence for which this holds. So don't worry about it. This D here will be very important. That's the limiting degree distribution. So that somehow the limiting, that describes the limiting proportion of vertices with given degrees. I'm also assuming that the average vertex degree converges to some limit. So that's the sparse setting that we've been interested in. In dense settings, this would blow up to infinity, which is not what we're going to be looking at. And these are my two assumptions, these A and B. And in terms of this, what an asymptotic power law is, it basically means that this limiting variable D here that we see obeys a power law. Okay? So now we've transformed basically the power laws, which are all about very large values in finite networks. That's hard. But if you've taken the infinite graph limit, then you can talk about power laws. Okay? So that's what this does. That's actually convenient. And it will also be very convenient later on to realize that these two conditions together imply that what is sometimes called the size bias distribution, where you multiply your probability mass function by its value and divide by the expectation, that's a probability distribution as well. And that actually converges to the size bias distribution of the limit. That follows from this weak convergence together with the convergence of the expectation. Now, it may not be totally obvious to you why this is necessary, why this is useful, but you'll see that later on. All right. So now about the fake news model in a bit more detail. What do we have? We have IID traversal times, which I'll denote by LEF and LER. They're IID over E, where E are the edges in my graph. And the LEF is the amount of time that the fake news would take to spread along an edge, whereas the LER is the amount of time that the correct news would take to spread across an edge. I'm assuming that these are IID over the different edges, but I'm not assuming that the two components of this vector are independent. They can have different distributions and they can be dependent upon each other. That's allowed. So then the fake news model, the fake news spreads using these traversal times LEF, and then the correct news spreads from the same source, but after a bit of delay. So what I'm thinking about is a proper news agent. It has sent out a message, realized it was wrong, and then sends out a correction a bit of time later after realizing that it was actually wrong. And it does so using these traversal times LER. And here's the positive, the optimistic component. Upon hearing the correct news, vertices are immediately convinced and start spreading the correct news only, and no longer the fake news. So the fake news has a bit of a head start. It sort of enters into the network, and depending on the network structure, it may get far, or it may not. But eventually it will be taken over by the correct news. And sort of the fake news is something like a second-class particle. You know, it enters the network, but it actually does not hamper the spread of the correct news at all. Okay? Now, what we'll be interested in is whether the fake news survives. How many people are going to, how many persons are going to be hearing the fake news? And here there's two ways how the fake news can survive. Weak survival means that the fake news reaches a growing number of vertices with positive probability. So with a strictly bounded from below probability, you will reach at least k vertices, where the constant in the probability is independent of the k. That's weak survival, yes?
How do you initialize? Is there one single node?
Yeah, there's one source. I'm taking that to be a uniform vertex in the graph.
And that one first spreads fake and then starts.
Yeah. Yeah, precisely. After a delay d. Actually, the delay d will not matter at all in the end. So weak survival is the fake news does escape, but it doesn't necessarily escape very far. Yeah, let me just.
Weak survival growing as the size of the graph, or
So. Okay, you're asking for details, right? The limit of n tending to infinity, and lim, I guess, inf, of the probability that fake news reaches k vertices, and then the lim inf as k tends to infinity is strictly positive. Okay? So with positive probability, you reach a number k, basically independent of k. Yes?
How does this spreading work? Is it like the broadcasting?
Yes, with IID traversal times, yes. So when you reach a node, that node will immediately start communicating, and it will use the traversal times of its neighboring edges to decide when it will jump across the edge. First passage percolation. But it's also called rumor broadcasting. It goes under different names. Was the answer clear?
yeah.
Yeah? Okay, so that's weak survival. And weak survival, as the name says, is relatively weak. The fake news will get away, but not very far necessarily. Strong survival is much stronger, and it actually means that the fake news reaches a positive proportion of the vertices with positive probability. So it basically goes viral. A positive proportion of the individuals on this planet has heard it. Okay? And then, of course, the main question is what the conditions are for fake news to survive, weakly or strongly. No? And that's what we're going to be discussing now. So first, weak survival. It's all related to the properties of our traversal times across the edges, the LR and the LF. And these LR and LF here are generic versions of the traversal times. So over the different E's, all the traversal times have these distributions, and they're I80. And apparently, it's useful to be looking at this particular moment generating function, which is the moment generating function of the difference of the spreading time of the correct news compared to the fake news. And then the first theorem, which is about weak survival, says that conditionally on the news originating in the giant component, as I said, I start my fake news from a uniform vertex. Now, I haven't said anything about there being a connected component, an infinite or a large connected component. That's the only case which is interesting. So there is a giant component in my configuration model, but if I take a uniform vertex, it could be outside of it or inside of it. And we're only interested in when it's inside, because when it's outside, it's basically in a very small component. Fake news can't travel anywhere. Okay? So my news starts in the large connected component in my graph. And then fake news survives weakly when either the spreading of the fake news is faster on average than the spreading of the correct news. That seems reasonable. But it can also be the other way around under a certain condition on this moment generating function. So you need to take an h for which the derivative of this function is equal to 0. And then phi of that h needs to be a parameter rho, which needs to be larger than some network parameter nu, which I'll explain a little bit more later on what it is. It's basically the expected forward degree of a half edge. And we need to assume that this phi is actually finite for some strictly positive s. That's the second part. That's actually the most complicated part of the theorem to be stating. And the second case, or the third case, is when the correct news spreads faster, but this moment generating function actually is infinite for all positive s. So that's a heavy-tailed distribution for the spreading. So that's yeah, very good. So you have an edge, E, and suppose that the fake or the correct news enters this, then the amount of time that it will take the news to spread will be this amount. So upon arrival here, the clock starts ticking, and when the clock goes beyond that LE of f, it will reach this vertex. So somehow slowly this edge is being traversed, and at this moment in time it will reach the other side for the fake news, and this for the correct news. Okay? Apart from that, the spread is exactly the same. Good question. I've gone too fast. So it's not quite a characterization. It leaves open one particular case that we haven't solved. And the one special case is where somehow this isn't quite working out. Namely, there is an S for which phi S is positive, but phi prime H of 0 does not have a solution. That is possible, but you really have to engineer it. And that's the only case that is not covered. So it's almost if and only if. Yes?
Is there like an interpretation, like real
Yeah, it's a bit complicated, but suppose you would be doing exactly the same on a tree, a branching process tree. Then you would get exactly the same feature. So it's basically giving you an explicit criterion for the spread of the slower, the later starting flow to catch up with the earlier started flow. Okay, and these conditions come up basically by looking at somehow what a flow of the two competing problems is along a long line. So, what?
That's a Q, right?
It is a Q, yeah. It's very closely related to queuing theory. It's not for nothing that Seva is involved. Yeah, but it branches, of course.
Right there is the fact that your momentary function fails to be as steep at that point.
Precisely. Yeah, absolutely. Yeah, so that actually means that there's no solution. Yeah, precisely. Yeah. So you basically track what happens along a long line. Well, basically the long line up to a uniform particle in a late generation. That's basically what's happening. Yeah.
So if I do correctly, that unless something is hidden under V, that this theorem does not depend on tau as long as it's in the interval from 2 to 3?
No, this is actually true for any degree distribution. I've not made any assumption. Not tau in between 2 and 3. We'll get to tau in between 2 and 3 a bit later on.
In general, it's not hidden here, and even for this, it's like valid for any configuration model graph.
Yeah.
Okay.
So for weak survival, there's an easy way of investigating it indeed. Okay. So as I said, it only leaves up one case, which I call pathological. So now let's think about strong survival, because I still have to convince you of the fact that it really is hard to kill fake news. So here we will be making assumptions about the precise degree distribution. So in particular, this does not apply for tau in between 2 and 3. And why is that? Well, we're assuming that I'm always doing the same thing, pressing the wrong button. So recall that if tau is in between 2 and 3, we have infinite variance. So that would actually suggest that this would blow up. But now I'm assuming that this second moment actually converges to something which is finite. So this is really tau larger than 3, if you want to think of it that way. And then what we're interested in is whether there's strong survival. And here it turns out that this is closely related to the exponential growth of certain continuous time branching processes. So these are called age-dependent branching processes. Who does not know what a branching process is? Very good. Who does not know what an age-dependent branching process is? Right, that's what I had expected. So you start with a regular branching process, but now you put time on the edges. You think of those as being birth times. Okay, so you have a root, it has a few children, and each of the children is born at a certain amount of time, and you assume that these birth times are IID. And then you do exactly the same for all your children. That's called an age-dependent process. And you're really studying it in continuous time. So you're keeping track of the number of alive individuals at a positive t in continuous time. Now, we all know that branching processes in general turn out to grow exponentially. That's true in the discrete world. We know that sort of in generation n, there's going to be nu to the power n individuals. And it turns out that is very similar here, but now it's exponential in the continuous variable t. And it turns out that these Malthusian parameters, which you can compute explicitly in this setting, describe exactly the exponential growth of your continuous time branching process, of your age-dependent branching process. So in this age-dependent branching process at time t, there's going to be roughly e to the power this lambda times t individuals that are alive. That's the interpretation. And you can imagine that if one has a lambda that is larger than the other, then it will grow exponentially faster, and therefore it will start occupying the entire space. So if that happens to be the correct news, then it will actually sort of take over the fake news. And if it's the fake news, then the fake news will get away before the correct news has any chance of taking it in. And that's exactly what you see here. So the largest lambda wins. So if that is lambda f, then the news survives strongly. If that is lambda r, that is the largest, then it does not survive strongly. What happens exactly at the equality is more difficult. And probably anything can happen. All right. So this is in the case where the inhomogeneity is relatively minor. So you don't have infinite variance degrees. So let's look at the next theorem, which is about the infinite variance setting. So here we're assuming that our degrees have an asymptotic power law with exponent tau in between 2 and 3, infinite variance. And we're even assuming, to make life a little bit easier, that our degrees are IAD. Okay? Then it turns out that the fake news survives strongly when this same age-dependent branching process with offspring distribution d star minus 1, this size bias distribution, and lifetime LF is explosive. So in this case, it turns out that the branching process grows very quickly, doubly exponentially. And if you look at the age-dependent process, it is actually such that it will reach infinitely many vertices in finite time. That is what is called explosive. Okay? The generations are going so quickly, and you will have so many values of the transmission times that are very small, that it becomes summable to basically reach generation n. It will become summable in n, and therefore basically the age-dependent branching process explodes. Okay? And the fake news survives strongly when its age-dependent branching process is explosive. Bear in mind, I'm not saying anything here about the branching process, the age-dependent branching process with the correct news. It's independent of that. That could be explosive, or it could not be explosive, or whenever this is explosive, actually the fake news has a chance of reaching a positive proportion of your network. So that's what we call, it is hard to kill fake news. Yes?
So when the way that you define the strong survival,
yeah,
doesn't rule out the strong survival of the network.
No, but the correct news will always strongly survive because it takes over the fake news, right? Its spread is actually totally independent of the fake news. So it will eventually basically see the entire graph or the entire giant component. Yes. So in a certain sense, the fake news is a second-class particle. It will be gobbled up by the correct news, but it does not gobble up the correct news. In fact, if I have time towards the end, I will say something about the other process where you really have competition. So if something is grabbed by one of the types, then it will remain on being that type forever.
My question was that you call this one strong and the other weak.
Yes.
It seems that they do not dominate each other.
That's a good question. In fact, we worked very hard for this particular theorem to prove that strong survival in terms of the conditions actually implies weak survival. From the definition, that's obvious. If you reach a positive proportion of your network, you're certainly going to be reaching k vertices for any k, right? Because the network has infinite size. So from the definition, it's obvious, but from the precise conditions, it's not so obvious. Because the conditions are so different. But it is true.
So even in this, because this was for this case, but for the second case, you don't condition on this R process, R distribution, and in weak survival, there was a condition on the R process.
Yeah, so that's the surprising part here. Here, it doesn't matter whether the LR process is explosive or not.
Yeah, I know, but earlier you said that sometimes for some R processes, actually weak survival is not met.
It's not met?
So if you came back to this weak survival condition.
Yeah. This one?
Yes. So, for example, you say, okay, this is where this weak survival is met. So, so then there is a case when fake news does not weakly survive, right?
Yeah, that's right.
This means that even
that's this case.
Yes. So even though here we have this condition involves R, actually for certain distributions of L, F, this condition would never happen, and those happen to be the same conditions that are.
So we can mathematically prove that the conditions for strong survival imply the conditions for weak survival when they make sense. Okay, so that's an analytical proof because the Malthusian parameter has a certain formula, and here you also see formulas. They're all in terms of moment generating functions, etc. So you can prove that one implies the other. So it's not possible to strongly survive and not weakly survive. That's obvious from the definition, but it actually also follows from the technical analytical assumptions that we're making.
So like what was surprising for me that in this condition you actually have this R distribution.
Yeah.
But I understand that for some F for which with strong survival happens, actually what R is in doesn't matter on also in weak condition.
Yeah.
Case.
Precisely. Yeah. Yeah. Indeed. All right. So that was strong survival, and this is why we called our paper "It's Hard to Kill Fake News," because if the thing does explode, and in many real-world networks we do seem to be seeing that tau is in between 2 and 3, this case. So if your fake news is explosive, even when on average it spreads much more slowly than the correct news, it still has a positive probability of actually reaching a positive proportion of the vertices. And this is due to the delay. And basically the idea is that the fake news can already have exploded before the correct news even gets started. That's the whole point. Yes?
So thinking about the consequences of this in the real world, so
yeah.
there are some studies that actually fake news travels much faster.
Yes. Yeah, we're not taking that into account at all.
Yeah, so even we don't need that. But the thing is like how realistic is the modeling assumptions about the explosive setting? Because if that part is also somewhat realistic.
Yeah, that's a very good question. One thing that I didn't say is in this setting, how often is such a process explosive? Well, for most of these traversal times, it will be explosive. And basically, the only setting where it's not explosive is where the traversal time of an edge is bounded from below by a positive constant. There are some other cases for which it's not explosive, but if you think about exponential distributions, any positive distribution that you can come up with, when it sort of gets infinitely small values, it will be explosive. So the boundary is something like a tail close to 0, that's like e to the power minus e to the power 1 over t. So, I mean, and then the tails are so thin that it's no longer explosive. But that's really very small. I've never seen such a distribution in the real world. So basically all distributions would be explosive. Of course, I'm assuming that all of these edge traversal times are IID. That may be one thing that you may wonder about. And I'm also assuming that my social network is a configuration model. That's also something that you may worry about. Okay, so in terms of applications, these are things that I would find much more debatable. Okay, I still have 17 minutes to say something about the proofs. You will probably not be surprised that there are some branching processes lurking here in the background, because I've been talking about lots of branching processes and they should come from somewhere. And where do they come from? Well, it turns out that my configuration model is special. It is what is sometimes being called locally tree-like. So that means that if you start from a vertex, very likely in your immediate surroundings, you're not going to be seeing any cycles. You're a tree, basically. And in fact, that tree is very well approximated by a certain branching process tree. This is how it goes. So you start from a uniform vertex. I was assuming that the source of my information spread is a uniform vertex. And it has degree distribution, d of u, and that actually converges in distribution to d because of my assumptions. I was assuming that the degree of a uniform vertex converges to this limiting degree distribution. That was my A assumption. But now I want to see how the spread further away goes. So I'm first going to be looking at all the neighbors of my original vertex. So there are du of them, and I take one of them, let's say A, and the law of the number of forward neighbors of A, which is the degree minus 1, bear in mind I'm using up one edge to get to this vertex, A. So if I want to sort of go further, I should not be using that edge. That's why the degree minus 1 becomes relevant. And if I denote that random variable by B of A, this degree of a neighbor minus 1, well, what is the probability that that value is equal to k? Well, then the the vertex to which I'm attaching my half edge, pairing my half edge, needs to have degree k plus 1, because I'm losing 1. And I need to be pairing to that vertex. But remember, I'm having my half edges and I'm pairing these uniformly at random. So I'm pairing my half edge to a uniformly chosen half edge. So if that vertex has degree k, then it's k times more likely to be chosen. That's where this extra factor k plus 1 comes from. This k plus 1 is just the same as the degree. So a vertex of the degree k plus 1 is k plus 1 times as likely to be chosen compared to a vertex of degree 1. Under my assumptions, this will actually converge to this limit. And if you look carefully, this turns out to be the size bias distribution minus 1. The minus 1 comes from the one edge that you're using in order to get to the vertex, and the size biasing comes from the fact that you uniformly pair half edges. All right, now I've done this for one neighbor, but actually for all neighbors that works exactly the same way. Yes?
So that locally you can ignore self-loops and double edges, right?
Yes. So for example, a self-loop, suppose you have degree 5. Then you have a probability 4 divided by the total number of half edges minus 1 to be creating a self-loop. But you're not going to do that in the initial stages of your process. And in fact, you're not going to be doing this up to time basically square root of n. So you're going to be avoiding self-loops and multiple edges for a very long time. And by that time, your description of your neighborhood has been so good that you can already you already know what is going to happen to your fake news spread or your correct news spread.
So, but I mean that this is probably a bit smaller, but significantly smaller, right?
Yeah, it's not clear whether it's smaller or larger, but it's a little different indeed.
Okay.
Yes.
Smaller
but it vanishes.
Actually less neighbors, but only.
Yes, it's an excellent question, but it's totally not obvious whether this stochastically decreases. In an Eindhoven random graph it does, but in a configuration model that's not clear. On average it does decrease, but okay. It's hard. Okay, so I was doing this for one neighbor, but of course you haven't been touching a large part of the graph yet when pairing this first half edge. And then sort of doing this again, you're going to be seeing that all the forward degrees of all your neighbors is going to be totally independent. It's basically an independent sample. And that's exactly what a branching process is, right? So all your neighbors have degrees that have asymptotically the same distribution and are going to be independent of this first one. That's true for the second one and the third, etc., etc. You can keep on doing this. And all of these give rise to a neighborhood that looks like a branching process with offspring distribution, this d star minus 1. Now we immediately see why this d star is very important, except of course for the root. The root is special. It has this degree distribution d. Okay, so this is sometimes called a unimodular branching process. Now how can you see the difference between the two settings where this was one of the cases that I was investigating for strong survival, and this was another case that I've been investigating? Well, here you have infinite variance, and that actually means that this size bias distribution has infinite mean. The second moment is something like the mean of the size bias distribution. So branching processes with infinite mean behave special, and they tend to grow double exponentially. So if you take a log and multiply that by something that decays exponentially, this will converge. So it grows extremely fast. Exponential growth is very fast, but double exponential growth, that's unimaginably fast. Okay? And that's also the reason why you get this explosive behavior. On the other hand, when the second moment is finite, then actually this branching process will have finite mean, and then we know that somehow the generation sizes grow exponentially. So that's much slower. Okay, when we're talking about rumor spread, forget about the fake news and the correct news. Just think about news spreading. There's no interaction between two different types of news. We're doing that in a way where the traversal times are IID across the edges. Now this is a problem that has been well investigated. It's called first passage percolation on the graph, sometimes also called the rumor spread models. And what you investigate there is something like the time it will take you to go from a certain source to a certain destination. And you can also investigate what happens sort of in time. So you look at how many vertices you're going to be reaching at a given time. Well, that's very well approximated by this age-dependent branching process, which could grow exponentially. That's what occurs here. So the number of vertices reached at a given time grows exponentially with time. In the infinite variance setting, it turns out that the number of vertices reached often explodes in finite time, basically meaning that you reach an infinite number of vertices, finite amount of time. That's a clear distinction between the two different cases. So there's a lot of work on these rumor spread models. Here's a few references. And how you deal with these settings is that you generally look at sort of, if you want to know how much time it takes to go from a certain source to a certain destination, you could say, I'm starting to sort of let the rumor spread start from this vertex all the way up to the moment that I reach my destination. That of course will work. However, our approximations to the branching process don't work so well when you apply the approximation many times. So it turns out to be much more convenient to be starting from the two sides simultaneously and grow them simultaneously. And then they will meet basically when each of them has size roughly square root of n. Since square root of n is much smaller than the network size, it means that you can still use the branching process approximations up to that size. So that's actually very convenient. So in this finite variance setting, we grow from two sides. For the fake news epidemic, we see when the two meet, then that would be the time that fake news would reach the destination if it isn't blocked by the correct news. Okay? So you sort of first look at the fake news exploration, ignoring the correct news, and then say, but you only reach it when none of the vertices along my path have actually been grabbed by the correct news before they were able to transmit their news across the edge. And that's what you then have to investigate. So fake news reaches the random destination when the fake news path is not blocked by the correct news. And that's where all the analysis goes into in investigating what the likelihood is of this fake news path being blocked. Now in the infinite variance case, the setting is much easier. So the amount of time to go between two vertices is basically the sum of the explosion time from this vertex plus the one on that vertex. So if you think about fake news or correct news, so the fake news will start, it will at a certain moment explode, and after explosion it will invade the graph very quickly. And in a little bit of time more, it will actually have invaded a positive proportion of the graph. It really is very fast. So suppose that the correct news is starting a bit later, and it hasn't exploded yet before the fake news has exploded. Well, then actually the fake news has already seen a positive proportion of the graph, and therefore you have strong survival. That's why only the explosion of the fake news process matters in this case. It's actually irrelevant whether the correct news explodes or not. It's simpler when it doesn't, then it will actually certainly survive strongly. So this is what I wanted to say about the proof. A little diversion. So as I was saying, in my fake news epidemic, if a vertex is reached by the fake news and then invaded by the correct news, it behaves as if it was always the correct news in the first place. It will start on spreading the correct news, and from there on, it will always keep on doing that. Now there's another a process that you could look at, which is more competitive-like, where you think of the two types, fake and correct news, as trying to explore the network and basically trying to occupy it. So in this setting, when a vertex is reached by one of the two types, it will always continue to spread the news from that type. It will not be invaded anymore by the other type. So this really is a competition problem. So you could think of this as being a model for marketing. Somehow people convince each other of buying a certain product or two competing products. The two competing products start somewhere, and each of these, the two starting points starts sort of to convince their neighbors to buy the same product, but people don't want to buy two products of the two different types. Think about Microsoft versus Apple computers or something like that. where it's quite expensive. Okay, so there's a big difference here in the sense that vertices, once occupied by a certain type, they will remain on being of that type forever. And then you can ask the question, yes, thanks. Then you can ask the question, who actually gets the majority of the graph? It's sort of a bit like this strong survival of the fake news. Okay, and here's the theorem. It basically says, again, in the setting where you have infinite variance degrees, that there's going to be one type that grabs the majority of the graph. That's the winning type. Okay, so either Microsoft wins or Apple wins, basically the entire graph. And the number of vertices for the losing type, the poor loser, converges in distribution. So that's just a finite number in the graph, even when the graph tends to infinity. In fact, with positive probability, that's just 1. Okay, so if the winning type happens to explode earlier, then it will actually grab basically the entire graph. And nothing is left over, or very little is left over for the competing type. So we call this the winner takes it all. And for those of you who know the song, the second part is the loser standing small. I thought at least that this was very appropriate because the paper is written with Mia Daven, who's Swedish. And who wins here, whether it's type 1 or type 2, is totally determined by the location of the starting point. And this is related to what real estate agents would call location, location, location. There's 3 things that are important for selling your house: location, location, location. All right. Conclusions? Or did you have a question?
After conclusion.
It's totally fine to do it now.
Yeah, so the question is, so this location, location, location.
Yeah.
I wanted to ask it earlier, but it seemed to me that in the original model, not this modified model, actually initial location did not matter.
Yes.
So
totally true.
Assumed this uniform distribution of the starting point, but I thought that maybe it's the same to say I can pick any point.
This is an excellent. This is an excellent.
Get the same.
This is an excellent question. We didn't do this in our paper, but now that you mention it, in this setting, the probability that fake news wins or strongly survives will turn to 1 when you start in a vertex of higher and higher degree. Because the delay is fixed. And if you let the degree become very large, your explosion will happen faster. And therefore, with high probability, fake news will explode before the delay is over. And therefore, fake news will actually strongly survive. So there is a relation, but bear in mind, in my setting, I'm always looking at positive probabilities, not at probabilities, I mean, not looking at how large they are. And they're always positive, but they do become larger depending on the location.
Yeah, because I was thinking about low degree nodes where all work, but then you have those high degree nodes that diminishing probability of being.
Yes, and we have to, right? Because we're assuming that there is a power law, so we have to have degrees of all scales. Yes. Yeah. Yeah. Yes. Excellent question. So, I mean, in this competition problems, there is a phase which is called coexistence, where the 2 competing types each get a proportion of the graph. And such settings do exist. It's just not in this setting. So there is a paper about something very similar, but then for exponential traversal times and finite variance degrees. And there, when the exponentials have the same parameter, you actually do get coexistence. So maybe that for the particular setting that I was talking about is a more appropriate modeling. Yeah, good question. Yes? In this very simple model, it is just the degree. But I mean, if you believe the spreading phenomenon being basically first passage percolation, then it should be the growth of your first passage percolation cluster. The exponential growth has a prefactor, which is a random variable. That random variable basically, to the largest extent, depends on your local neighborhood. So for the configuration model, that means your degree. But for other, well, it's probably even not just your degree, but also the degrees of your neighbors count. So it's a bit more than just degree. Yes? Yeah, so as I was saying, there is a paper on the exponential setting for the light-tailed case. And there you can have coexistence when the exponentials have the same parameter. But when they have different parameters, it's still the fastest that will win. Yes? I missed the first part of your sentence.
Centrality measure based
on
the explosion of the first percolation.
Interesting.
Optimal starting point.
I didn't even know. You should give me the reference. Interesting.
There's a diffusion centrality.
Yeah, but diffusion or first passage percolation may be entirely different things, because diffusion is more about random walks, I would say. Whereas first passage percolation is really SI epidemic, a bit of a different model. Okay, conclusions. I'm over time. Even when at a disadvantage, fake news can reach a positive proportion of the vertices in the network. Being at a disadvantage means that its expected traversal time of an edge is actually larger than what it would be for correct news. That's what I dubbed, the same problem again. It's hard to kill fake news. Weak survival is basically determined by the expected edge traversal times. There was a little bit more of a discussion, but this was basically it. Whereas strong survival is determined either by the explosion for infinite variance degrees or the Malthusian parameter, the exponential growth parameter, for finite variance degrees. Thank you very much.
Thank you very much for fantastic talk. So, I don't know, quick questions or?
There were a lot of questions already, which was very nice.